This project is presented by shefail Ahmed, souradip biswas and stanzin choldan. The name of our project is Li-Fi technology. In conventional communication technology, we use light or electromagnetic wave for communication, but here in Li-Fi, light fidelity, we are using light to transmit data. The objective of making this project was to get our hands on this technology. This technology has been under research for several years, and few commercial devices are also available based on this technology in the market. However, it still haven't got that much of attention. So we made a hardware project which gives much more insight of the technology rather than in simulation, and hardware also gives much more opportunity to learn. We did this project by ourselves and successfully tested the concept of Li-Fi technology. We also wanted to implement this technology in our day-to-day life. In this slide, you will see all the components we have used. We have used two Arduino boards, one is Uno and the other one is Nano. We have used a solar panel which you will see further in our project, and we have laser light, IR LEDs, photo detectors and photodiodes which will be used to detect and transmit light. And as of the software, we are using Arduino IDE for coding these Arduino boards. In this circuit diagram, you can see Arduino Nano board used as the transmitter. It is using an IR LED, and on the other hand, we can see the Arduino Uno used as a receiver. So here we can see the IR receiver. This circuit diagram will be used for both demo and testing of our project. Now coming on to testing, our first objective was to select an optimal transmitter as well as a receiver. So we had IR LED and laser light as an option for our transmitter, and for receiver we had LDR and photodiode. We tried different combinations with our circuit like LED with LDR and LED with IR and many other combinations, amongst which we found IR LED with photodiode the most optimal, since IR and photodiode showed maximum response to the input signal. For testing purposes, we wanted to have the transmitter and receiver with highest response. We wanted the fall time and rise time of the pulse to be as small as possible. Unfortunately, we did not have access to an oscilloscope, so we were not able to check the response time of these components. So we tried to use the serial monitor on an Arduino. We connected those components onto the Arduino as per our circuit and plotted those graphs onto the Arduino serial monitor. According to the graph, we found out IR receiver had the least rise and fall period, and it was much more responsive than counterparts which were LDR and photodiodes. The working principle of our project is quite simple. Whenever there is light or the light is on, it is binary 1, or whenever the light is off, it is binary 0. So this data is encoded and decoded to transmit data and convert the received data into characters.
And again we have the transmitter code on the left and the receiver code on the right. So inside the code we can see that we have defined an LED pin that will be our ion transmitter LED, and it is defined as digital pin 12, and we have also the period, that is the time period of every pulse. It is defined as 15 milliseconds, and continuing with it, it cannot be 15. Yes, so now we have the transmitter code on the left and the receiver code on the right. So in this code we can see that we have defined a LED pin as 12, and that will be our transmitter LED, and the period is 50. So this period is a time period of every pulse, that is 1 or 0. And inside the function of the setup we can see that we are just initializing the serial monitor, and we are also printing some messages. Here you can see we are writing the LED pin that is turning off the LED, so that it will indicate that there is transmission of message inside the loop. Sorry, we can see that we are searching this for serial string. So whenever we enter any kind of string into the serial monitor and we press enter the string, it will detected here, and it will send into variable named as input INP, and then the new line character which will be at the end of this line will be removed, and we will call this send message function. So inside the send magazines function, we can see that every loop we are looping through each and every character of the string, and we are calling this send byte function. So this send byte function does some manipulation to extract each and every bit out of it, and also these bits are then transmitted if the bit is one of them. Then the LED pin is lighting up, or if it is 0, then the LED pin is turned off. So you can see if we are also delaying for the period and we are returning to a send message function. So after all the messages, all the characters have been sent, we are just digital writing the LED pin to low, that is we are sending a null character, and it will also indicate that the message has been ended. And finally we are printing. Okay, so now we can take a look at the receiver's code, and here again we are just initializing the serial monitor, and then we can see inside the loop that we are having two variables, that is the current state and the previous state. So current state is getting its value from LDR function. LDR function is taking input from the analog grid from analog pin 0. So analog pin 0 is having the photodiode, and whenever the photodiode voltage is greater than the threshold voltage, it will return false, or if it is less than the voltage threshold, then it will return true. So we are having this function if we are checking for the if condition. If the current state is 1 and the previous state was 0, that is we will have detected a risking edge, and then we will enter the segment of code, and we will light the digital pin LED high. So this LED pin just for indicating that the green light LED, that the transmission of bits has been started. And then we will delay for 1.5 into period, and we will delay get into a loop, and inside the loop we can see we are calling the get byte function, and the get byte function just loops for 8 times, and it gets each and every character value from LDR. And if it is 0 or 1 or 0 accordingly, it is storing into a character. So we are delaying for period after transmission of each bit, and then finally we are just storing the character into a variable, and then we are returning. So here we have the character is a null character. Then we can see that the transmission of a bit has been ended, and we can just print out the message. And if it is not null, so we can just update our message string, and in further we can perform the incrementation it with character received. And finally we have the after all we have the received all the characters, and we can come out of the loop and just print the message onto the screen. And also you can see for the transmitter that we are having a Arduino Nano connected here with the USB 0 port, and on the other hand for the receiver we have we can quickly upload both of these codes into Arduino. So you can see hello for transmitter 1 Arduino, and hello for receiver 2, and we can start by sending some message like.
So we are using the same 8 mega 328 peak microcontrollers on both the Arduino boards, and the clock frequencies also the same, but are running some certain commands like the serial commands or executing the programs at different times on both Arduino boards. So whenever I run these programs, it takes different times for both the Arduino boards, and this can be observed in our, and this induces an error in the transmissions of bytes. So for example, now you can see that time period is 50 milliseconds, and now if I transmit it 10 byte data, so you can see the data is being transmitted. And now if we compare the data, you can see that after like till the 8 byte, the data is transmitting perfectly, but after that you can see that it should be receiving a 9 here, but it is receiving 8 because its last bit is not getting received. So it is skip 1 and skip 1, and then continue to receiving the bits from 0. So the receiver is missing some bits, and this happens with the time periods. At the time periods this will happen more often. So you can say only 8 bits are transferring perfectly and there is a bit missing, and then again for the next 8 bytes we are receiving perfectly fine data. So if I reduce the periods of the pulse, so for example if I just upgrade it to the 15, now it is the 15 millisecond pulse, and now if I try to send the same data, so here I will be transmitting the 10 byte data, so the transmission is much faster. But as you can see, only 4 bytes are getting transmitted uh, perfectly, and after that we are having an error. So the receiver is missing a bit after the 4 bytes, and as we decrease the periods, the number of bytes getting transmitted correctly are reducing, and if we increase the time periods of the transmissions will get slower, but also the intervals after which we have error bits increases. So this is happening due to certain unsynchronization between the clocks. So since we have the same synchronized clocks in the beginning, but the clock intervals are different for both the Arduino boards, after some times the receiver is missing a byte, this induces error. So that there are many ways to solve these problems, but what we are doing in this project is we are detecting after how many numbers of bytes or how many bytes we are receiving an error bit. So after, for example, if we are receiving some 3 bytes, we are receiving an error bit, so we can just send a null collectors after the bits so that the clock will be synchronized again. So we'll be sending data from this to the intervals, and then we will send a null character so that the receiver will again in synchronize with the transmitters, and then we will are again sending 3 bits, and this loop continue till we have received all the data. And more thing is that earlier that we are doing this in the receivers, you can see we are ending our message whenever we receive a null characters. But now using the updated codes, now we will be ending the message when we will be update when we will receive a new line characters. So now let us now update the code on the both the Arduino boards. So as you can see, the transmitted message on the left side is almost same as the code we have earlier, but there is only a few only on the slide difference, that whenever there is a when we cross an error bit, that is a bit every third bit, there is every third bit we are having an error bit. So after every third bit we are just waiting, and this waiting time is just to send a null character. So we are waiting for a periods of 10, and we are setting the lead pin to the low. That means we are sending a null characters, and then we are again writing the lead pins to the high. That means that we are sending a starting bits. That means we are again transmitting the message in the receiving. uh, you can see there is no longer ending whenever, and we get a message as a null to whenever we get a message null, it will be treated as a break that we are, yeah, we are just synchronizing the clocks, and we won't print anything. But if you receive new line characters, now we can say that yeah, the message uh, is received, and we can print the message, and also print some other things as well. And the rest of the code is same as it was earlier. Now let's just upload the code here. So yeah, you can see the transmitter to and receiver to are having so now I can transmit the 10 bytes. Okay, so you can see that after every 3 bytes we are having a null characters just for the synchronizations of the clocks, and after that the data starts again, and the receiving of a data starts again, and you can see the message is perfectly fine and there is no error in the message.
We can also send large messages. For example, let me just send a demo message here. So it is a long string, it will take some time. Yeah, so now the message have been received, and you can see that the message does not contain any kind of error, and you can see 1424 bits have been transferred, and the time taken is 900 milliseconds, that is 19 seconds, and this is the speed. So one thing we have to keep in mind is that the components and the microcontrollers we are using are not made for such high response time applications. So for communicating with high response time, we need much better receptors and transmitters. So this is the circuit diagram for music streaming. We have a 3.5 mm jack connected to our mobile phone playing music, and we also have a laser light driven by a 5-volt power supply. The analog output coming from the headphone jack will modulate the laser light, which will be received by a solar panel. The solar panel is connected to a stereo speaker using an aux cable. Thus, it will play music according to the received signal. However, there is a lot of noise into the output because of the visible light in our room. In order to reduce the noise, we can either turn the lights off, or we can cover up the area of solar panel which is not being penetrated by the laser. The Wi-Fi technology has a great potential to be applicable in our daily lives, but it requires high receivers and transmitters. It is also in questionable use when no data loss is tolerable, for example, in transfer of files. However, it can be applicable in broadcasting audio and video streaming where multiple devices can receive audio and video data, for example, in a stadium. To compete with Wi-Fi or other kind of technologies, it needs more research and experimentation.